Alright, welcome back Year 11. Today we're going to be looking at Boyle's Law. So what we did last lesson was about the ideal gas and what is an ideal gas. Today we're going to be talking about one of the assumptions or one of the observations we can make because of that ideal gas assumption we created. Do now has 3 questions. Define particle diagrams of a substance. Define the term density, and then last one is explain why solid substances cannot be compressed. Now this goes back on to what we did last lesson when we first introduced gases and some properties of gases. I'm going to skip ahead to the answers now, and it's up to you to pause for you to have a go at these. So draw the particle diagrams of a solid, liquid, and gas substance. This is what you'll get. You'll see that the solids are very much compacted together side by side. You'll have the liquids, they're quite tightly compact together, but they also have a bit more room to vibrate and move around. And then you have the gas particles. They're just bouncing off and moving in all sorts of directions. Remember, for a gas particle, the motion is random, and it is also always in straight lines. So they're always bouncing off in straight lines, but very randomized. Question 2, define the term density. Okay, so density, if you look at this, the formula they used to teach you back in probably in year 7, year 8, density of a substance is equal to the mass over volume. So the mass over volume equals density. So if we have more mass in a given amount of space, then the objects will be more compact together. So what we have here is solids is the most dense. So solids has the greatest density, as you can see. And gas, as you can see, there's a lot of free space and not many gas particles, so that is the less dense. Okay, so try to write that down into a nice little sentence. Density refers to the amount of particles within a given volume of space. Based on the diagram from question I, because the question does ask you to refer back to it, solid particles are most compact together and therefore have the highest density. Last one is explain why solid substances cannot be compressed. As you can see, one of the properties we talked about with gases is the fact that there is a lot of empty space. There's a lot of empty space with the gases. A lot of empty space here, 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 here. So with all that empty space, you can push down on these gas particles. You can almost push down on this container, and all this empty space will allow these particles to move towards it. If you try this exact same process with solids, that's not possible, because there is no free space between these solid particles. If you push down on these particles, there's really no direction that these particles can go. So the reason why solid particles cannot be compressed is essentially there's no free space. So even if you apply a great amount of force, the particles cannot move, they cannot be compressed. Now one of the interesting features is, if you do apply enough pressure, you can change a solid into its liquid state, but obviously you're changing its states, you're not really retaining the same state of matter. So what we're looking at today is inquiry question 4. How does the ideal gas law relate to all other gas laws? The gas law we're looking at today is Boyles Law, and we will briefly talk about a concept from Charles without explicitly saying it's Charles' law. So what I want you to do is copy this down into your book. This is your lesson intention, and this is your success criteria. We're trying to investigate the mathematical relationships that exist between the gas laws, and we're going to try and describe how these gas laws relate to each other using measurements such as volume, pressure, temperature, and the quantity of gas present. Quantity of gas meaning by how many moles of gas are present. So firstly, what is an ideal gas? We talked about this last lesson. Gases firstly are very complicated. The purpose of our model here is just to allow us to predict certain behaviors of real gas, but we are making assumptions that they are ideal, meaning by they have these features. It doesn't necessarily mean they all have it. So number one is gas molecules always has constant and random motion. So it always has constant random motion. So it's always moving in all directions. Gases don't attract or repel each other. So if I had a container and I just let the gas move around, they'll just move in all random directions, always moving, but always random. They'll never get attracted to each other, so you never see them pair up. The only type of collision that they will have is elastic collisions. So no energy is lost between collisions. When they collide to each other, they just bounce right off. And then in the fourth assumption is any space they occupy is assumed to be zero in volume, so negligible. The gas molecules are so small that whatever space they have occupied is basically zero volume. We can show this through a simulation. So if I go to my simulation on the PhET website and I click on ideal gases, so if I just pump a bit of gas particles in here, this is essentially how the ideal gas is assumed, or the model is assumed. We're assuming that these particles are bouncing or colliding elastically, so they just bounce right off each other, as you can see here. We also said that the amount of pressure on the container is dependent on the actual collisions the particle makes onto the surface. So as you can see, every time these particles bump onto the surface, there is a change in pressure. The average kinetic energy of the system will change the overall temperature. As you can see, temperature hasn't changed. If I add more particles, there's more pressure. Temperature still hasn't changed, which means the average kinetic energy, so the average motion between these particles, is still the same as before. So that's the assumptions we make with this model here. As you can see, also these particles are occupying a very small amount of space. Okay, so that's also why we assume that their volume is negligible. So there we have that. That's just recapping on what we learnt about the ideal gases. And then the next part is looking into the gas laws. So the gas laws is just a mathematical relationship used to describe the relationship between the volume, the pressure, the temperature, and the amount of gas particles you have in a certain system. As you can see, these are essentially the three gas laws we're going to look at. Also, just to note, a scientific law represents something that's always observable. So, contrary to how they teach you in legal studies or whatever, a law doesn't mean it's definite, it just means it's always observable. It's one of the interesting things that people get confused with if you have a non-scientific background is scientific law doesn't mean it's true per se. It essentially means it's something you can continuously observe, and that's what a scientific law actually means. Alright, so the first relationship we're looking at is this one here. V for volume, P for pressure. These other two here, we're going to be looking at it later on. So the man who came up with this gas law, and he was the very first person to come up with the gas law, is Boyle's law, or Robert Boyle. So this is the man over here, and he came up with an interesting relationship about how volume of a system changes depending on the amount of pressure you are exerting onto the gases, assuming that the amount of gases stay the same and the temperature you're doing this experiment stays the same. So let's have a look at this little animation here. We have a balloon and a syringe. We have a person who has placed his finger over the opening of the syringe to create a closed system. What can you see that's happening on the balloon? Well, firstly, I can see that the balloon's volume, so the volume of the balloon, is decreasing. It's going down. Okay. I'll also notice that the pressure of the syringe applying onto my balloon is increasing. So the pressure is increasing. So by increasing pressure, I'm decreasing the volume in my balloon. That's what he saw. And like I said, Robert Boyle's observation, the Boyles law, or any scientific law, is something that you can always observe. Okay? So this is what we have here. And why will we have that? Because a simple explanation for it is when you have a syringe or any kind of closed system and you have a little balloon, if you increase the pressure, so if the pressure is coming down a lot harder, what actually happens is the little gas particles inside that syringe, so long as you block it off, that's going to exert a greater amount of air pressure, if we could say, air pressure onto the balloon. And so if there's a greater amount of air pressure being applied on the outer surface of the balloon, the only place the particles can go inside the balloon is to go further inside. So that's kind of the explanation of Boyle's law. Why does increasing pressure end up decreasing the volume of an object inside that system? Next, we have another simulation to actually show for this relationship. So if you just be a little bit patient and I'll bump this up. Alright, so this is a second simulation here. I'll also make sure these are linked below so you can find them. So this next one, we're not doing Charles' law. The next one we're doing is Boyle's law. So Boyle's law is a relationship between volume and pressure, assuming the amount of particles we have stays the same and the temperature stays the same in this process. So that's what we're going to go for. Now let's just say I increase the pressure like we were talking about before. So if I'm increasing pressure, increase pressure to about, let's say, 2 atmospheric pressures. Okay, let's calculate the volume we have. As you can see, the pressure is 2 atmospheric pressures, and then my volume has essentially halved. So at 1 atmospheric pressure, my volume was 3. At 2 atmospheric pressures, I was half of that, so 1.5. So assuming that it doubles for each time, let's see what happens if we change the pressure to 3. let's add data point. Let's try and, so we can't really get it up to 3 unfortunately, but if we calculate, you can see right there. So again, 2.03. Ooh, looks like I changed it slightly. Let me just change that up again. So add pressure of 2, calculate, add new data, calculate there. Okay, so there's the actual true data there. If I add another point, let's try and decrease the pressure down again. So let's have it at 1.5, 2 liters. Okay, and then if I add a 5th data point, remember whenever you're trying to graph anything, 5 data points is usually the best because that actually gives you some kind of a trend. What I've been trying to do is actually graph out a relationship. As you can see here, it kind of looks like a little curve, or it's starting to curve. So let's try and put it down over here at a really low atmospheric pressure. At a really low atmospheric pressure. Let's see what happens to the volume on our graph. Let's calculate that. Alright, so as you can see, this comes down like this. Okay, so it's a curve that comes down like this. If I try and draw out that curve, so if I try and work it out over here, so what we have was essentially crafted out, and it kind of curves down like this. As you can see, the curve itself never comes close to 0. So remembering what I learned from high school maths, this is a hyperbola graph, or hyperbola graph. Okay. If you want to see this in action, in terms of an actual video, there's this one also here. So this is a vacuum chamber, essentially a little glass, so like a glass chamber where all the air has been virtually taken out. That's to increase the air pressure. When they release the air pressure, you'll see the balloon start increasing its mass. So I'll link that as well for you to see. So this is the relationship we have, Boyles law. So we're saying if the given amount of gas is constant and the amount of temperature of that system, or the temperature is kept constant, the volume of the gas is inversely proportional to the pressure. So if it's a hyperbola, right, it's inversely proportional. Okay, so that's the formula there. Please write that down. And what we also mean by inversely proportional, if I assume that K, my constant, if I just leave that B, K, I'll just move that away. So essentially P is inversely proportional to V. Okay, how did I do that? I essentially moved P over, so it looked like V equals 2 K over P. But because K is a constant, we can even assume that it's just 1. So we say that V is proportional to 1 over P. This sign here means it's proportional to something. Okay, pressure is the SI units for pressure. In this case is usually given in kilopascals. We do have some questions that aren't kilopascals, but that's okay. We have volume, which is always given in liters. So there you have that. So pause this video now if you want to copy down the notes. Another scenario we can come up with is this bit. So what if it was the exact same syringe, but then we changed the volume? So how do I work out what's the new volume, what's the new pressure if I changed the pressure or the volume? So this is the very first syringe, and then this is syringe number 2. Exact same method, so exact same amount of particles, but now I've essentially increased pressure. Pressure has now increased. So what is my new volume? Volume 2. Okay, so this is what we have. So we have volume 1 and we have pressure 1. So whatever pressure that's going down there. We skip ahead. We've increased the amount of pressure. So we've increased the amount of pressure. The new pressure we have is pressure 2. According to Boyle's law, if we change the pressure, the volume is inversely proportional to the increase of pressure. So volume 2. Well, we know that K is constant. Okay, so K is always going to be the same number regardless of how you change the pressures. So we can write a nice little mathematical equation. P1 times V1 equals to K equals to P2 V2, which means the pressure and volume of the first system, that ratio will still stay the same as the pressure and volume of the second system. So the ratios are the same. Doesn't mean the pressure and volume will stay the same though. But because the common factor is K, I can essentially make these two equations equal to each other. So I can rewrite the equation and write this. So this is the alternative equation we can end up writing because of this relationship and the fact that K is just a constant ratio. Alright, next one is to do the calculations. So you have been warned there will be some spoilers on these questions. Please pause the video now. I'll give you 5 seconds before we move on to the actual answers. Alright, I will be moving on the answers now. So, question 1 asks, what's the new tire pressure if you compress the tire and its new volume is now 10.6 liters? This is just using what we copied down just then. The formula you're dealing with is P1V1 equals to P2V2. Now a good way of going about this is to substitute it straight into the formula first and then rearrange the numbers. The way the HSC actually works is you are given marks for the correct substitution. So they're always trying to give you marks. So do the things that will get you marks, help the marker out, substitute things in first, and then manipulate your equation. So what I did here was I already identified what P1V1 was. So here we go. That is V1. That is P1. And then I also identified what V2 is. Okay. As you can see in this question, pressure was in pound force per square inch. So it's not in kilopascals, but that's okay because the answer we're trying to find for the pressure is still in the same unit, so we don't have to change it. If the question asked find this in kilopascals, then obviously you'll have to change it. So substitute that, manipulate that, and then that was my final answer. My final answer is based off the smallest two significant or the smallest significant figures in the question, which was 44. So 2 significant figures. There was 2 significant figures there. So my final answer needs to also be in 2 sig figs. Next one we have is the pressure. So pressure P1, volume is 5 liters, that's V1. And then we have a pressure of P2. What we're trying to find is what V2 is. If I put that through, so 1 times 5 equals to 0.3, and then V2. So rearrange that and you get 17 liters. Again, 2 sig figs is the smallest number or small significant figure in my question, so I'll also make sure I have that for my answer. Okay, Boyles Law Calculation 3 and 4. Have a look at that. Pause the video now, and then I'll go through the answers in 5 seconds. Alright, so here are the answers here. So the answer you should get, just substituting those numbers through, rearranging it, you should get your answers to 0.375 liters. Okay, so that's volume 1, pressure 1, and then we're trying to find V2 because we know what P2 is. So 0.375 liters. If you have a look at the question again, 20 degrees Celsius, that's in 2 significant figures, so that's why I also rounded off to 2 significant figures. So 0.38 liters. This sign is just the approximation, so that's the actual equal, so what it's actually equal to, that's what the approximation you've made based on the significant figures of the question. Number 4, so again, you're just putting in your substitutions, so a sample of 2.3 liters, that's V1. You have a pressure of P1, and you have a pressure of P2. You need to find what V2 is. Again, remember, Boyle's law only really works if the amount of gas stays the same, so the amount of mass of the gas stays the same, or the amount of particles available stays the same, and the temperature stays the same. So substitute that in. That was the answer I got. Really big, long number. Read through the question again. How many significant figures, or what's the lowest significant figures of the question? And it comes back down to being just 2. So I just round that off to the nearest 2 significant figures, as that's 8, so I round up, so I get 0.95 liters as my answer. So let's look at some applications of Boyle's law. Boyle's law, you have weather balloons. So weather balloons are really great. You actually attach a little device onto the balloon itself. It's used to measure temperature, humidity, atmospheric pressure to an altitude of about 25 kilometers up in the atmosphere. One of the great things is in terms of how we measure wind speed, as you can see on like those weather channels or weather reports. Basically, when the balloon is in the air, there is a GPS system attached onto that balloon, and where that balloon ends up moving, that will give you firstly the wind speed of the balloon, because the balloon obviously doesn't generate its own speed around the curve of the Earth, and also gives you the direction of that wind. So that's actually how they end up measuring wind speed. It's actually using these weather balloons, allowing it to fly away, and just measuring what speed it's flying away in and in what direction it's flying away in. And then obviously the last one is the actual application to Boyle's law. So the higher it goes, up into the atmosphere, you have less atmospheric pressure, which means the volume of the balloon will increase. So it will allow the balloon to reach a higher altitude as we go, or it allows the balloon to just gain in volume as it goes higher altitude. And then until a point where the balloon itself, the surface of the balloon cannot contain the expanding gas, it pops, it will burst, and then the instruments just fall back down to Earth. In terms of how they actually end up collecting those equipment back, or do they intend to collect the equipment back, I'm not too sure. I assume they would want to collect it back, but I'm not too sure how they actually go about doing that. So there's that little weather balloon, all the way up we go. And that's the little device. Also, when it does pop, they do use a parachute, so when it's fallen back down, the actual device that they're using to measure the weather doesn't break. So the parachute is at least there to ensure it doesn't break apart as it's falling. Another application of Boyle's law is obviously when you're flying up in the air on a plane, on a little plane. Whoa. Is when you go to different air pressures, you'll feel that your ears start to narrow down, clog up, popping sensation. And that's because when you reach higher altitudes, your ear canal pressure, the air pressure here, if I just show you, your ear pressure here, okay, decreases. So, or increases, sorry. So as you reach high altitudes, the pressure drops. So So pressure drops here. The air pressure here is still the same. So the pressure hasn't changed. So why do you get that sort of painful sensation? It's because the pressure between your ear canal and this little tube here, they're not equal to each other. And when they're not equal, that's what causes that little bit of air pressure pain when you're in the air, or maybe if you're going up a really high escalator, or elevator, sorry. That's how. So how can you fix it? Well, a bit of chewing, a bit of swallowing can help. Should be help. Can help open up the tube and allow the air to flow. So once the air does flow, so a bit of chewing, a bit of swallowing allows the air here to flow between the two sites. Then they finally reach or regulate each other and reach a certain point where the air pressure is the same on both sides. And that's kind of how you end up curing that pain.
And that concludes our lesson today, where we talked about the different types of properties of gases. In our next lesson, we're going to actually start looking at ideal gas laws. So what we brought in today about the kinetic molecular theory, we're going to be applying that to the three gas laws: Boyles Law, Gay-Lussac, and Avogadro. Until then, I will see you next time. Oh, let's not forget Charles' Law as well. But yeah, until next time, take care.